So, greetings from Canada. So, I'm calling you right now around midnight my time. So, let me talk about camera and AI white balance. So, when you take a photo, we often think that what you see on the screen is exactly what's in the physical world. So, you look with your camera, and what you see through the screen is what you see with your eye. But your camera actually has many processing steps that are applied to produce that image on your screen, right? This photo. And we call this a pipeline because these steps are applied one after the other, and it just continuously does this while you're looking at the image. So today what I want to talk about is one of the most crucial steps on your camera is known as white balance. So white balance is a very simple step, but if you don't get it right, your image won't look good. So this is very important for your color in your image. So let me just give you an example. So if you look here, if I was to change the white balance, you would notice that the image changes and you get what we call a color cast. And this is not desirable. So it's very important to make sure that your auto white balance is correct so the image color looks correct. So what I want to do today is explain to you, why do we need white balance? Why does the camera have to do this? You don't have to do it as a human. You're not white balancing, but the camera needs to. And then I'll tell you how we can use AI to do auto white balance for cameras. So to understand white balance, we actually have to first understand a little bit about color. So when you look at a tomato, you just look at it and you get this sensation, oh, that's the color red. So let's think about, how do you really do that? So in the physical world, there's no colors. The tomato isn't red. The tomato is actually reflecting electromagnetic radiation. So the physical world is full of magnetic radiation, from gamma rays to X-rays, ultraviolet, and there's a certain range that's known as the visible spectrum in terms of wavelengths. So when you're looking at a tomato, you're not looking at the color red, you're looking at its reflectance of the spectra. So you could imagine that this tomato reflects spectrum, the visible light spectrum, like this. So we call this a power spectral distribution. Now that comes into your eye, and your eye has three cells that act like sensors. And we call these the short, medium, and long cone cells. And these respond to different electromagnetic radiation differently. So the short one responds to this region, the medium this region, and long this latter region. So what happens is, when this radiation comes into your eye, these cells respond and you get these sensations. So the short one responds a little bit to this region because there's not much radiation there, medium a bit more, and long even more. And that produces this sensation of red. Oh, I see red. Now, cameras have similar mechanism that mimics the human eye. So what we do in cameras is we put these filters on top of the pixels that are somewhat like the short, medium, and long. Different sensors have different filters. So you can see they're not perfect. It doesn't exactly match the human eye. And so that means that the sensor will perceive the color of the tomato slightly different. So what we can do is, in the factory, we can calibrate that sensor and its response to the incoming light. And it's not very complicated, just a simple 3x3 linear matrix that you can calibrate that takes the sensor response and maps it to human perception. But we haven't really seen the whole story, because what is this reflecting? So here I say, well, the tomato is reflecting light like this, but what about the light? So what you're really doing is you're looking at the tomato under some illumination, let's say sunlight or indoor light. And that illumination has its own spectra. So actually what's coming into your eye is the reflectance of the tomato reflecting the environment lighting. And so you don't actually get this into your eye, this spectra here, you get a slight variation on it based on the lighting. Now, what's really interesting is you can observe the tomato under many different lighting conditions. Sunlight, different types of indoor light. Even you'll see sunlight changes. So noon versus dusk versus dawn will be slightly different. Now, the question is, does it change how you perceive the tomato? So I would think that all of you agree that when you look at a tomato, it always looks red. So you have an amazing ability to correct for this. So your visual system compensates for this different illumination. And this ability to see objects under different illumination, but as the same color, is known as color constancy. Now, this has been well known for many years, and there's a mathematical model called the von Kries transform. So what Johann von Kries figured out was somehow your brain, working with your eye and its response to long, medium, and short, can figure out, determine what is the environment lighting, and it divides that out. So it's just a simple division. If you have some lighting, you kind of detect what the lighting is, and you just divide out that lighting, so you correct for any different lighting. And I'm going to do an example. So this example is from Andrew Stockman. He's a very famous professor who works in human perception, and is this very nice example to kind of demonstrate color constancy. So what I want you to do is I want you to look right at this point, and I'm going to count to 10. But what I'm going to do is I'm going to show you a different image. So keep looking here. Look right at the same spot, and I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when I go back, this image should look more constant. Now, if you close your eyes and maybe look away and look back, you'll realize the image actually had, let me just go back to another slide. You can see that it had this color cast in it. So by just looking at this, this is kind of mimicking the color constancy ability in this demo. Now, the problem is cameras can't do this. So your camera, when it sees a tomato under different illuminations, it actually has the color cast in that image, the sensor image. So we have to correct this, and this is white balance. Now, sometimes in the academic world, we would call it computational color constancy. So if we get this correct, then we can remove this color cast, and so the image will look, the colors will look correct, and the colors of things like tomatoes and skin tones will be proper. Now, how does white balance work? Well, the first thing you have to do is, given this sensor image, you have to detect what is the overall illumination. Once you detect that color, you can correct it. So this is essentially the von Kries transform. So we apply von Kries transform to every image that comes into your eye. So that's white balance. Now, if we think about the problem, the challenge is actually this part. How do you detect the illumination? So the pipeline, your auto white balance is, do illumination estimation, you get out the color from the sensor, and you divide it out. But if I give you just a general image, and I say, here's an image, tell me what is the illumination, it's not an easy task. And you have to do this no matter what type of image you're looking at. Now, digital cameras have been around for a long time, so there's lots of examples of auto white balance. But what I'm going to talk about today, and these are different methods, and some of these methods we still use, but of course, everything's moving towards AI. AI right now gives the best results, so I'm going to talk to you a little bit about AI methods. So again, this is the processing chain for auto white balance. The image comes in, you estimate the illumination, and then you correct it. So essentially what we're going to do is we're going to replace this with some sort of neural model, an AI model. Now, before we start, we should think about, how do you get training data for this, right? We need to supervise this model. So one of the things we have to do when we work on AI white balance is we have to capture training data. So we tend to go outside and indoors, and we take a camera, and what we do is we place these charts, we call these calibration patterns, inside the scene. So we know that these patterns are white, but because of the color cast, we know that this is incorrect. So whatever this white is reflecting, that must be the illumination. So we go in and we manually click on these regions to get the ground truth of the illumination for that image. Now, the problem is, if you don't mark this out, your AI network will learn to detect where the color chart is in the image. So at training time, what we do is we actually mask out the region that has the color chart in it. So when we train, we do validation, we do testing, you have to feed it images that mask this out. Now, The very first successful AI white balance algorithm came out in 2017, and this was done at Microsoft with one of my old colleagues, Stephen Lin. I was really just starting up, especially the deep learning AI. We had these convolutional networks. So what this team did is they took the AlexNet, one of the original very successful deep networks for images, and they cut off the end and they modified, we call the head of the network to predict the illumination. And if you look at what the network actually learned, it learned how to identify in the image regions that were reflecting light. So it tended to learn where the white regions in the image were. So here you can see it's learning, oh, this region here looks like it's very a good predictor of the illumination. This region here, this white shirt is a good predictor. And it also estimated local illumination. So when you combine these two, what it thinks is local versus the region it thinks is white, it's a very good predictor for the actual color of the illumination. Now, the problem with these early generations, and this is one of the first papers, there were many, the problem is that the networks were just too big. So the networks tend to be 500,000 to 5 million parameters. In fact, I was just at a conference earlier this year. I saw an example and it was 25 million parameters network. Now that may be small compared to a large language model, but remember, this is something that's being applied to every image that's coming in, right? You have your video, you're moving it. So we have to do this very quickly. So even 5,000 parameters, or sorry, 500,000, 50,000 parameters or 500K parameters is too much. So we need lightweight AI models to do this. So I'm going to talk about two papers that came out of our lab that work on this a problem that tried to give lightweight AI auto white balance. So the first work that we looked at was called this two camera illumination estimation. And what was happening at this time, and now we're all very used to this, is our cameras have multiple, or our smartphones have multiple cameras. So we wanted to use this fact that we have more than one camera to be able to do the white balance. So I'll show you the basic idea. Now, remember, you have two cameras, you're looking at the same scene. Now, the camera sensors on your cameras are different. So one of your cameras, maybe your wide angle, will be one sensor with one set of spectral sensitivities to light, and let's say the telephoto will have a different spectral sensitivity. So that means even though they're looking at the same scene, in this case, the tomato, the colors of those two different sensors are slightly different. Now, under the same illumination, you can compute a transform that tells you how to transform this sensor into that sensor in terms of color. The color, this is just like how we calibrated the camera earlier. Now, what if I change the illumination though? Well, if I change the illumination, because these sensors are all slightly different, that transform will change. So now we see that the transform between these two cameras is related to the scene color, and it's also related to the illumination. Now, this observation was made almost 20 years ago in a little bit different context by Graham Finlayson. At that time, though, first smartphones weren't very popular, and smartphones only had a single camera. So we realized we could use this observation to do it for modern cameras. So again, what we're exploiting here is that under different illuminations, this simple 3x3 matrix, so 9 parameters, is encoding up the change in the illumination. That means that these 9 parameters can be used as a feature to a neural network. So what we did is we developed this system that took 2 of the cameras, we would turn them on at the same time, we would align them. So this, let's say this is your normal camera and this is your telephoto, or this is, sorry, your wide angle camera. We would crop out the region, we would downsample them, so the images are very small, and we would very quickly compute this transform that aligns these two images in terms of color. Now, this transform, 9 parameters, is what we feed into our neural network. So our network's very, very simple, but it's very good at predicting the white balance. Now, to be able to get the training data, we needed to be able to ground truth these images. So we built this little setup where we put a color chart, a calibration pattern on this pole, and we would go out and take images. So this would be your main camera at the wide angle, And I know it's a little bit hard to see here, but you can see this is the color chart, and here's the color chart. Same here. So this gives us the ability to ground truth, to know what the illumination is in both of these images. Now, what we can do is when we apply our algorithm, we can compare it with many existing white balance algorithms, including some of these early white balances I mentioned to you, like Gray World from like 1980. Now, when we do the comparison for white balance, what we do is when we measure the illumination from the ground truth, you can think of that as a vector in RGB space. So when you estimate your illuminant, the error that we typically measure is the angular error. How different are these two vectors? If the angular error was 0, that means you're 100% accurate. So what you can see is compared to all of these methods, our two-camera white balance method gave the best results. But what's even more interesting is our network is so simple that we only had 200 parameters. So compared to these other deep networks that have, 500,000 to 5 million parameters, we only have 200 parameters, and we can do this very quickly. Let me show you one other example, or another work that we did in our lab, and this is known as time-aware white balance. Now, the observation here is that at different times of the day, you're more likely to see different types of illuminations. And so what you're seeing here is the illuminants up here in these little circles. These are outdoor illuminations like sunlight, shadows, and these are indoor illuminations. So for instance, right now for me, and one reason I'm a little bit tired and speaking slowly is because it's midnight. So at midnight, there's not much outdoor illumination. So this gives us a lot of information about what we're likely to see. So what we did is, in addition to the neural network, we also keep the time of day. So under noon, the same environment. Under sunset, the color illumination will be slightly different. So let me explain a little bit more about time of day. So when I talk about time of day, you just think about the sun coming up and going down. And you can see here that the sensor response to this different type of illumination will be slightly different. So it's not just the clock time, it's also related to your location. So at 7 p.m. in July, if I'm in New Delhi versus Toronto, I'm going to have a different sun profile. So maybe one's going to be dusk and the other is still going to be the sun's high in the sky. So what we do is we take not just the clock time, we take the geolocation and we convert that into a probability of the type of condition, dawn, sunrise, and so on. And we had to capture a data set that also had this information in it. So we had to capture a new data set that has this time and geolocation. And then what we do is we still use the colors as a feature to predict the illumination, but we also embed in the time. And not surprisingly, what happens is, again, using angular error, we get some of the best results. But what's really nice is because we have this additional feature, we have a very small model, only 50, in this case, 5,000 parameters. So very good performance, only 5,000 parameters. And in this case, we don't have to turn on two cameras. We just simply look at the time and we look at the geolocation. Okay, so white balance, I hope you understand it a little bit better. It's a critical step that you have to apply for every image that you take. And if you don't get it right, the image colors will look incorrect. And I talked about two methods that came out of our lab here at Samsung in Toronto, where we looked at ways we can use additional information to have very lightweight AI white balance methods. Okay, so thank you very much.